What do we do? Yeah, that's right. We did factoring stuffs. Right? Okay, cool. Today, do you guys have questions on what we did last time? Pretty straightforward, right? Hopefully. All right. Well, today we're going to start talking about trig identities. So when we talk about an identity, we're talking about an equality statement that's valid for all values of a variable. So for example, like a pretty dumb identity would be something like 2x plus 6 equals 2 times x plus 3, right? Like, well, that's always true, no matter what the value of x is. That's not particularly informative because it's pretty narrow, but that's something. What we're going to be doing in section 1 here is we're just going to kind of be building out some of these sorts of relationships, but they involve trigonometric things like sine, cosine, tangent, etc. Now, some of these identities that we're going to build out here today are going to be kind of stuff that we've already talked about that we're just going to formalize into an identity. And some of them are kind of new that we'll construct or piece together from other things that we have kind of talked about already. The first set of identities are going to be called the reciprocal identities. So if you remember way back to chapter 2, we talked about sine, cosine, and tangent, and then we defined cosecant, secant, and cotangent, right? What was the relationship between, say, sine and cosecant? They were reciprocals, right? So, and the same thing with with secant and cosine, and with tangent and cotangent, right? So we're going to formalize those into what we're called the reciprocal identities, and just say the following, that sine is 1 over cosecant and cosecant is 1 over sine, and so on and so forth for all of these. So again, that's no big deal. That's just kind of taking an idea that we'd already talked about and kind of formalizing it, writing it as an identity. Just FYI, the identities that I'm going to be listing here today, I've already put into a separate sheet. See the basic identity sheet here in your OneNote? That's got all the identities that we're going to talk about today kind of all grouped together in one place for you. Just FYI. Okay, doke. Okay. So our next block of identities. Remember back on the unit circle. How did we find tangent on the unit circle? Y over x, great. And on the unit circle, what's y? Sine. What's x? Cosine. So we can say that tangent is really sine over cosine, right? And if tangent and cosine are reciprocals, what would I say that cotangent is? Cosine over sine. So we'll call those the quotient identities, those two right there. So again, these are things that we kind of intuitively already had talked about. We're just kind of formalizing them as an identity. But this is not new information per se. Let's imagine now that we have a right triangle. Let's call this angle theta. So if we think about like, it's a right triangle, so we can think about SOHCAHTOA, right? So this side here would be the adjacent side. This would be the opposite side, and this would be the hypotenuse. Everybody cool with that? And using SOHCAHTOA, then we'd say that sine theta would be opposite over hypotenuse, and say like cosine theta would be adjacent over hypotenuse. Right? This is just like way back chapter 2, just kind of restating some stuff. Well, let's see what happens when we talk about sine squared theta plus cosine squared theta. Well, sine theta is opposite over hypotenuse. So sine squared theta is going to be opposite over hypotenuse squared. Similarly, cosine squared theta will be adjacent over hypotenuse squared. Does that feel okay to everybody? How do we square a fraction then? We have opposite over hypotenuse squared. How do I square a fraction? Nope. That's okay. If you have 1/2 squared, what do you get? 1/2 squared is just 1/2 times 1/2, right? Which is, or 1/4, right? So what did we end up doing? We squared the top. 1 squared is 1. And we squared the bottom. 2 squared is 4. Everybody agree with that? So what's opposite over hypotenuse squared going to be? Yeah, opposite squared over hypotenuse squared. That's right. And we can make or say the same thing about adjacent over hypotenuse squared. Is everybody okay there? Notice that we have a common denominator on that fraction, right? Both fractions are over hypotenuse squared. So we can write that as a single fraction. What's opposite squared plus adjacent squared have to be? What's that have to equal? Go back to our picture. What is opposite? That's a side, it's one of the legs of a right triangle, correct? What's adjacent? The other leg of our right triangle. So using the Pythagorean theorem, we know that opposite squared plus adjacent squared has to equal hypotenuse squared, right? That's just the Pythagorean theorem. And what's that going to simplify down to then? Hypotenuse squared divided by hypotenuse squared. 5 divided by 5? It's just 1, right? Hypotenuse squared divided by hypotenuse squared? It's just 1. So that will become an identity. So these identities that we're talking about now all get the name the Pythagorean identities because the Pythagorean theorem was a fundamental part of kind of developing that identity. So let's say we start with this sine squared theta plus cosine squared theta is equal to 1. We know that's true. And let's say we divide both sides by sine squared theta. When I divide the left-hand side by sine squared, I know division is distributive. So I can really just divide each term by sine squared theta. When I do that, what is sine squared theta divided by sine squared theta equal? 1. Okay. What's cosine squared theta divided by sine squared theta? So if we go back, if we look at our identities, remember that cotangent is cosine theta over sine theta, right? Everybody's cool with that? So what is cosine squared theta over sine squared theta going to be? Absolutely, cotangent squared. Very good. And what is 1 over sine squared theta going to be? Well, if I go back and I look, 1 over sine is cosecant. So 1 over sine squared is going to be cosecant squared. Very good. That's another Pythagorean identity. Now let's say that instead of in our first step where we divided by sine squared theta, what if instead we had divided by cosine squared theta? What's sine squared theta divided by cosine squared theta going to be? See if you can figure that out on your own for a moment. Anybody got it? Sine squared theta divided by cosine squared theta. Elise, what did you say? Go ahead. So what's the worst that's going to happen? Is it you're wrong? What's the big deal? I say things that are wrong all the time. Just take that risk. Throw it out there. Ava. Yes! Was that what you were going to say? You should have taken the risk. You could have looked smart in front of everybody. That's okay. I heard you say the right answer. That's why I called on you. I saw you sub-vocalize it. I wasn't trying to embarrass you. I was giving you trying to give you an opportunity.
Well, I didn't know.
That's okay. But again, like, what's the worst that's going to happen? I mean, like, nope. Oh, well. Try again. Cosine squared theta divided by cosine squared theta is 1. Okay. What is 1 over cosine squared theta going to be? Secant squared theta. Very good. That'll be our third Pythagorean identity. So just go ahead and drop those in there, printed out, or in a nice typed out format there to match with the other stuff that we did. There we go. Okay. So here's an observation for you. We've been using the unit circle a lot, right? Have you noticed how, like, cosine of 30 degrees is like root 3 over 2, and sine of 60 degrees is also root 3 over 2? And how, like, cosine of 60 degrees is 1/2, but sine of 30 degrees is also 1/2? Or how about how, like, cosine of 45 degrees is equal to root 2 over 2, but sine of 45 degrees is also equal to root 2 over 2? Or that, like, cosine of 0 degrees is equal to 1, and sine of 90 degrees is also equal to 1. If we go and we look at all of these pairs of angles, what do you notice about all these angle pairs? What do you notice about all those pairs of angles there that I've color-coded? $30 and $60, $60 and $30, $45 and $45, $0 and $90. What do they all add up to? They all add up to 180, 360, 30 plus 60 is? 60 plus 30 is? 45 plus 45 is? 0 and 90 is? They all add up to 90 degrees. Do you remember what that's called in geometry? When two angles add up to 90 degrees? See? Yeah! There it is. So those are all complementary angles. All right. So have you noticed how we spell these things, where we have like cosine, and then we have sine? We have like cosecant, and then we have a regular secant. We have cotangent, and then we have tangent. You ever wonder what the co prefix is? It's short for complementary, because what we're noticing is that, like, cosine of theta equals sine of the complement of theta, right? That cosine of 30 is equal to sine of 60, right? So how do we formalize the complement of theta? Is mathematics. How do I write that in symbols? What's the complement of theta? How do I write that symbolically? About 90 minus theta, right? If theta is 30 degrees, its complement should be 90 minus 30, or 60 degrees, right? Now, in trigonometry, do we use degrees more often, or do we use radians? Radians, okay. What's 90 degrees in terms of radians? Do you remember? Think about the unit circle. Where's 90 degrees at the unit circle? What's that radian measure? Well, not the coordinate. The coordinate is 0, 1. That's true. But like, you know, like we just did this. Like, what's to here? How many radians is that? Pi over 2, right?
What's that word with C?
Complementary?
Oh, and the parentheses?
Complement of?
Oh.
Yeah, I just messy. Okay. All right. So we have that. Oops. So let's put this together now. So I can say the following. Cosine theta is equal to sine of the complement. Cotangent theta is equal to tangent of its complement. Cosecant theta is equal to the secant of its complement. Yada, yada, yada. That's all we're saying here, right? Sorry. That's nice, right? Maybe we didn't notice that explicitly, but like after I pointed out to you, it's like, oh yeah, I guess that's been happening a lot, hasn't it? All right. Last set of identities, and then we'll do some examples. So recall back to chapter 1. Remember in chapter 1 we talked about odd and even functions? Right? That was something we talked about. An odd function, we said, was something where f of negative x equals negative f of x. And we said an even function was something where f of negative x is equal to f of x. You guys remember that? At least vaguely? It's like, okay, that looks familiar. We did that. Now remember back to chapter 3 when we talked about the graphs for sine and cosine and tangent. Remember when we did that, one of the things that we identified was the symmetries. We remember that sine, we said, was an odd function. And we also said tangent was an odd function. But cosine was an even function. What about cosecant, secant, and cotangent? Well, guess what? If sine was an odd function, what do you think its reciprocal is going to be? Still odd. Since tangent's an odd function, what do you think its reciprocal is going to be? Still odd. Cosine's an even function. What do you think its reciprocal is going to be? Even. So, since sine is an odd function, the same property of odd function should apply, that sine of negative x should give me negative sine of x. That's an identity. I can do that for all of the odds and all of the evens. I can just apply those properties, and I'll get, oops, that wasn't where I wanted that to show up at. I get these odd-even identities. That are just a natural consequence of our definitions of odd and even, and the fact that certain functions were odd and even. All right. So let's do some examples now of how we can use these things. Okay. All right, first example, it says find sine theta if tangent theta is equal to 3 and cosine is negative. If you remember, this was actually something we did back in chapter 2. So let's kind of recall what we did back in chapter 2 to do this. So first thing we want to do is identify what quadrant the terminal side of theta needs to lie in. Cosine is negative in what quadrants? 2 and 3, very good. Because cosine is the same as the x-coordinate, and the x-coordinate's negative in quadrants 2 and 3. Tangent theta equals 3 means tangent is positive. What quadrants can tangent be positive in? 1 and 3, very good. Remember, tangent is y over x. So y over x is going to be positive when both y and x have the same sign. If they're both positive, like in quadrant 1, y over x is positive. If they're both negative, like in quadrant 3, y over x would be negative. Or would be over positive. Y over x would be positive. So where's my answer got to be at? Quadrant 3. So we'll draw ourselves a picture. So there's my theta. Now I remember that tangent is y over x. And I know in this case tangent is equal to 3, which I can think of as just 3 over 1. Right? Bless you. So what can I say about x and y? X should be 1 and y is 1, right? Or x is 1 and y is 3, excuse me. Is that cool? But what quadrant is our answer in? 3. So really, what should I be writing here? -1 and -3. Okay. So this picture that I've drawn, what definition of sine, cosine, and tangent am I using? This is a point on the terminal side. right? Notice it's not a unit circle because we are not 1 unit away from the origin. So in this definition, sine theta is y over r, where r is this length from that point to the origin. Okay, so I just need to calculate r and then plug it into my formula, right? How do I calculate the distance there from a point to the origin? Use the distance formula, right? Don't huff and puff at me. We did this already. What do you notice is happening here, though? What's the coordinate for the origin? 0, 0, right? So what's this just turning into? Looks like the Pythagorean theorem, doesn't it? Oh, yeah. Everybody's okay there? So what is sine theta going to be? Y, which is -3, over r, which is the square root of 10. And then we'd probably rationalize our denominator and write that as negative square root 10 over 10. Woo! Mr. Kulik. Yikesies. Well, okay. Guess what? We can do the same thing, this time using identities. So let's see. The first thing I want to do is I want to find an identity that relates tangent and cosine together, but just tangent and cosine together. So, okay, let's go back through our identities. Let's see, tangent and cosine, nothing there. Tangent and cosine, nothing there. Tangent and cosine, nothing there. But this is pretty close. Why is that pretty close? Oh boy. Why is this pretty close to tangent and cosine? Because secant is 1 over cosine, right? So far, that's my best option. Continue back here. Tangent and cosine, nothing. Tangent and cosine, nothing in there. So I'm going to be using this guy right there. So I know that tangent theta is 3. One plus 3 squared is 10. Now to solve for secant, I would square root both sides. When I square root both sides, that creates a plus or minus. And then secant is 1 over cosine. And if I do the reciprocal to both sides, I say that cosine is plus or minus 1 over the square root of 10. But what do I know about cosine from the problem? It's negative, so what is that telling me about the plus or minus? Has to be the negative one. Great. So now that I know what cosine is, I can go back here and look for an identity that involves cosine, tangent, and sine. Can I find one that involves all three of them? Well, since I was paying very close attention, there's only one set of identities that involve three. It's the quotient identities. And I see here that tangent is equal to sine theta over cosine theta. That'll do. Just color code it. We're trying to find sine, so I'll multiply both sides by cosine theta to get the sine theta by itself. Cosine, we just found, was negative 1 over the square root of 10. Tangent, we're told in the problem, is 3. If I multiply those together, I get negative 3 over square root 10. And then we probably rationalize our denominator. And we have the same answer that we did before. What was the major advantage of using the identities versus the previous method? Well, there's no picture, right? At no point did I have to draw a picture. Did I have to worry about what quadrant something was in? It was not geometrical at all. This was purely algebraic. What was the hardest part about using this method? Figuring out which identity I needed to use, right? But once I did that, this was pretty much just like plugging stuff into formulas, right? Which is kind of nice. All right. The other type of problem that we'll be doing in this section will be simplifying an expression involving these trig functions. So when we're doing a simplifying problem like this, there's two things that we can use. We can do algebra stuff, like foiling and factoring and making common denominators and combining like terms. Algebra stuff. The other thing we can use are identities. Everybody okay? Those are the two kinds of tools that we have to work with. Algebra stuff, factoring, foiling, combining like terms, common denominators, stuff like that. Or foiling, or identities, identities. Typically, my recommendation is to do look for an algebra thing to do first and look for identities second. Everybody okay with that? All right. So let's look at this guy. It says sine cubed x plus sine x times cosine squared x. Does anybody see an algebra thing I can do here? Take the x out. Okay, so the x is like, sine x is one thing. It's not like sine times x. It'd be like if I had square root x plus square root x times square root y, you'd be like, oh, I'll factor off the square root symbol. Like you can't do that. Like the square root symbol is like attached to the x. Here the sine is the attached to the x. But you have the right idea, because there is something in common with the two terms, right? I have one term here and one term there. What is in common between them? Sine x, right? Does everybody agree with that? So that is what I'd want to do first, is I'm going to factor out a greatest common factor of sine x. When I factor a sine x off, what does sine cubed x turn into? Sine squared x. Very good. And what does sine x cosine squared x turn into? Cosine squared x. Very good. It doesn't really matter. I used a bracket because I have all these other parentheses there. It just gets a little parenthesis heavy. Means the same thing. I think it's easier to kind of see what happened if I made a bracket there instead of a parenthesis. Matt? Sure. Okay. Got that. Everybody cool with what we did? Now let's look to see if there's any, and this has been improvement, right? I went from something that had two terms, because I had two things added together, to something that was one term. It's just two things that are being multiplied together. So that is an improvement. Does anybody see an identity that we can use? You should take a flip back through your identities. See if there's anything that sticks out. This thing that we're doing right now tends to be kind of difficult for students the first time going through. It's typically difficult because there's not like one set of instructions on how to do something. You have to there's lots of different things you could do. Some of them are helpful and some of them are not helpful at all. It takes some time and practice to develop some intuition. Cheyenne, you have an idea?
What a question on that.
Okay.
How'd you take sine x out cosine x?
I didn't, but this is sine x times cosine x squared.
Okay.
So like when I divide this term by sine x, that piece just goes away.
Okay.
Right? Imagine this instead was just like x cubed plus xy squared.
Oh, okay.
Right? If we factor an x off, it's kind of the same thing, right?
Okay.
Does that,
Yeah.
you see that what happened? Okay. Anybody with an identity idea? I'll give you a hint then. Look at the Pythagoreans. Look at the Pythagorean identities. Excellent. So Alexis says that sine squared plus cosine squared, which we have right here, is just equal to 1. What's sine x times 1? Sine x times 1? Sine x. Yeah. And that's as good as you're going to be able to do because you got it down to one thing. In general, when I see something here where I have like trig things squared plus or minus something, almost always I'm going to be wanting to use a Pythagorean identity. Like that's going to be almost my first order of business is going to be to start looking at those. All right, let's do another. I got lots of these. All right. First thing Mr. Kulik suggests to look for is algebra things, like factoring, foiling, common denominators, combining like terms. Anybody see an algebra thing I can do for this one? Should be pretty obvious. Ava.
So if you like multiply the sine x squared or this sine squared x, or you put it on the other side, like wouldn't that cancel out the?
Well, there's not another side. This is just like one fraction. It's not like an equation that equals something. So that's not where we're going. What should you do with this? Foil, right? That's just a foil problem, isn't it? Everybody agree? And look at the setup of that FOIL problem. Secant x minus 1 times secant x plus 1. That fits one of our multiplication patterns from last time, doesn't it? Isn't that a difference of 2 squares multiplication pattern? So I don't even really need to FOIL this out. I know that that's going to, if this is like a minus b and this is a plus b, it's got to multiply out to give me a squared minus b squared. Is everybody okay with what we saw there? The execution? Notice I'm trying to take big pauses here and let you kind of absorb what happened. Right? I'm taking big pauses before when I'm asking you and then answering these questions. I want you to think about it. Okay, this is how we're going to develop some intuition so we have ideas of like what to do here. Because it's not just like, here is procedure, follow procedure, just be a robot. These aren't robot questions. You do need a little bit of intuition, a little bit of forethought. You need to have seen what has happened before and what you can do or what you'd want to do in situations. Okay, so we did our algebra thing. We did some foiling. Anything else algebraic left to do? We've got this now as a single fraction, still a single fraction. Did we combine any like term? Are there any like terms to combine? No. So we're probably done here, right? If I do any factoring, I'm just going to write it back the way it was, which is not helpful because it wasn't helpful before. So what should I do now that I've exhausted any algebraic things to do? Identities. Great. Should I be looking for an identity in the numerator or the denominator? Which one is more complicated? The numerator, because there's subtraction going on up there as well. There's 2 terms up there. So ideally, that's where I'm going to be looking for to use an identity. So notice it here what I have. I have something squared and then plus or minus minus 1, right? Where should I be looking at my identities? What identity should I be looking for? I have something squared and then it's being added or subtracted. Pythagoreans. Does anybody see one that we can use here? Here, notice secant squared is equal to 1 plus tangent squared, right? I have a secant squared. So I'm going to replace that with 1 plus tangent squared. But Mr. Kulak, isn't that making it worse? Now we have 3 terms instead of 2. That's less simple than it was before. Yeah, but look at what can happen now. I have 1 plus tangent squared x minus 1. What can happen? The plus 1 and minus 1 cancel out. Oh! Yeah, that did make it better now. Okay. So I have now tangent squared x over sine squared x. Nothing algebraic to do there because it's still just, that's like one fraction. Go ahead. Is there an identity that I could use though that could be helpful? Is there a way to rewrite tangent so that it has a sine in it? Or a way to rewrite sine so that it has a tangent in it? Look at the quotient identities. Tangent is sine over cosine. Oh, okay. So what I'm going to do is I'm going to think about this fraction as the product of 2 things. I'm going to think about it like that. Because I'm going to rewrite now tangent squared x as sine squared x over cosine squared x. Why was that helpful? What can happen? The sine squareds cancel, right? Everybody's okay with that? That's how we reduce fractions when we multiply, right? Go back to like middle school or elementary school math when you multiplied fractions. So those things cancel out. What am I left with now? What's left? Important question. Somebody be brave. Take a stab. What do we have left? Take those risks. The worst thing that can happen is you're wrong. It's no big deal. Then you get useful information. You figure out that, oh, that was wrong. Right? And you were brave. You'd be the bravest you've ever been. Bunch of cowards. We have a 1 left on top and a cosine squared on the bottom. Woof, Mr. Kulik, that was so hard. Oh, yeah.
So can you just explain after you like fix the identity, like how you got all those fractions?
So, yeah. So we had this, right? I wrote that just as the numerator over 1 times 1 over the denominator, right? Then I said tangent squared is the same as sine squared over cosine squared. This thing is still just there. And then I canceled the signs. And then I'm at 1 over cosine squared. Does that feel okay? Perfectly reasonable thing to ask if you're confused or you're like, I'm not sure I followed all that. Like, say something. We can go back and like talk through it again, nice and slow. If you're real specific like that and are like, that's where I got lost at, that helps me even more, right? Okay, 1 over cosine squared can do better than that. Is there an identity I can use to shrink that down even further? Obviously, there's nothing algebraic I can do. Anybody see it? There is an identity to use here. Yeah, you can write it as secant squared because it's 1 over cosine squared. And that's as good as we can do. We got it down to a single thing. I got more examples. Let's do another one. Bloop. All right. Simplify the expression. Cosine x over 1 minus sine x over cosine x. First thing we like to do is algebra. Great. So what do we have going on here? We have 2 fractions that are being subtracted. Algebraically, what can we do with that? What was that? No. Why not? It's a subtraction symbol, not a multiplication symbol. So we can't reduce across addition and subtraction, only multiplication. What else could we try then? That's a good guess though, right? It looks like something we've done before, but the detail is different. It's an important detail, but it's a good thing to like get a clarification on. So I'm glad that you volunteered a guess. Even if it was wrong, it was an important thing to be wrong because it gave us a real thing to correct, right? So I'm really happy that you guessed that, even though it wasn't correct. That was good. That accomplished something that's a common mistake. We got a chance to talk about it. Great. What else might we do with these 2 fractions that are being subtracted? What if we just had like 2/3 minus 3/5? What would you need to do that problem? What should we do for this problem? A common denominator. Yeah. Okay. Important question. What will the common denominator be between cosine x over 1 minus sine x and sine x over cosine x? What will that common denominator be? Between 3 and 5, what's the common denominator? 15, 3 times 5, right? Why is it just 3 times 5? Because 3 and 5 are relatively prime. They have no common factor between them. Everybody agree with that? Is there a common factor between 1 minus sine x and cosine x? Nope. There's no common factor between them. So what should the common denominator be? 1 minus sine x times cosine x. Is everybody okay with that? So what do I need to multiply 1 or cosine x over 1 minus sine x by to make that common denominator? Cosine x over cosine x. What do I need to multiply sine x over cosine x by to make that common denominator? Yes, 1 minus sine x over 1 minus sine x. Very good. So when I multiply cosine x times cosine x, what do I get? Cosine squared x. Great. And then I have my minus sign. Well, let's maybe not write that yet. And then I'm going to distribute. But when I distribute, I have to make sure I'm distributing that negative sine x through. What's negative sine x times 1? Negative sine x. Yep. And then what's negative sine x times negative sine x? Positive sine squared x. Yep. And then my denominator. Should I multiply my denominator out or not? Mr. Kulik says not. Let me explain why. When I reduce a fraction, it must be in factored form to be able to reduce. Look at the denominator as I've written it without doing the multiplication. Is it in factored form? Yeah. If I multiplied it out after I combine like terms in the numerator or whatever I need to do up there, I just would have to factor the denominator back to where it's at right now if I was going to try to reduce. So like, why would I multiply it out? In general, don't multiply denominators out. Unless you have a good reason to do it. I wouldn't. Everybody's okay? All right, let's look at the numerator then. We've done our algebra thing. Are there any like terms to combine in the numerator? Nope. Okay, well, let's look for an identity then. What do you see going on up there? Where should we be? What identity should we be looking at? Do you see things that are squared? They're being added or subtracted? Pythagorean, exactly. Which one? There is one we can use. Yeah. Is that what I have here? Does it matter that they're not written next to each other? No. They're being added. It's fine. So sine squared plus cosine squared is 1. Oops. Everybody's okay with what happened there? Okay. Do you see anything to do now? Now, at least you sub-vocalize something. Can I call on you to see what it was? Yes.
1 minus sine of x in the numerator and
Yes. Yes, exactly right. Those can reduce. They are 100% identical. They're being multiplied. So it's in a factored form. So we absolutely can reduce here. What do we get after we've reduced that? No. 1 over cosine x. Remember, look at where the cosine is. It's in the denominator, right? When we cross things off, do they disappear? Not technically. They technically turn into 1. Ava.
How did the numerator become 1 minus sine x?
So sine squared plus cosine squared is 1. And then the minus sign is still just the minus sign. It wasn't there. Okay. 1 over cosine. Can we do better than that? It is secant x. And that's as good as you can do. Still doing okay? Does this feel like it's starting to get any easier? I know these are tricky. All right. What about this one? Simplify the expression sine x times cosecant negative x. Is there anything algebraic to do here? I say no too, right? There's nothing algebraic to do here. Just have two things being multiplied together. Like, can't multiply them together because they're not like terms, so nothing algebraic to do. Okay? So identity, right? What identity do I want to start with? There is kind of a right answer here. What about the cosecant? I wouldn't do that yet. And the reason I wouldn't do that yet is look at the variables. One of them's an x, the other's a negative x. The first thing I'd want to do is I want to get them both to be either both x or both negative x. Which one do you think would be easier to get to? Both regular x's, right?
Oh, yeah.
So what identities do I have that take a negative x and turn it into like a regular x? Those are the odd-even identities. So let's go back and look at those. That is what I'm going to use. Cosecant negative x is equal to negative cosecant x. Everybody cool? Now, Bella, now I'm going to mess with the cosecant. What is cosecant? 1 over sine. Yep, that's okay. So I'm going to have sine x over 1 times negative 1 over sine. Everybody's okay there? What can I do with that? I'm sorry. You said something and I just missed it.
Combine like terms from sine x minus sine x remaining.
So combine like terms. Yeah, I would just cancel, right?
Oh, okay. I thought you would bring over the sine x.
I mean, you could. You'd write it as negative sine x over positive sine x.
Okay.
And you get? -1, right? That's okay. Yeah, it's okay to think about it that way. I would have been, usually I reduce before I multiply. Tends to make life easier than if you multiply and then reduce. In general. Okay, I have one more example, and then we're all done for today. Yay! All right. Let's take a look at this one. Cosine of pi over 2 minus y times the quantity cosine or cotangent y plus tangent y. Ugh. Any algebraic thing here to do? I mean, there's one thing you could do. You could say, okay, I'm going to distribute like this thing. But does that seem like a good idea to do?
No, it's too much.
Yeah. What are we going to want to do before we do anything, even think about distributing that? I'm using identity, get rid of that pi over 2 minus y piece, right? Using the co-function identity, what does that turn into? Sine, well, it would be y in this case, because that's the variable. Everybody's okay there? Okay. Again, you could multiply the sign through here. I probably wouldn't bother with it because you're going to turn it into two terms instead of how it's currently written as one term. I'd probably just leave it, me personally, but you could multiply it through if you wanted to. I wouldn't. I would go for an identity here. And I would actually probably go for two identities here. Notice that nothing is squared, so I'm not going to be using any of the Pythagoreans. So it's either reciprocal or quotient identities are really what I'd be looking at here. It doesn't really matter which one. I would probably take cotangent and tangent and rewrite them using the quotient identities. So cotangent is cosine over sine. And tangent is sine over cosine. And what am I going to need to do with those two fractions? I have two fractions that are being added. What do I need to do that? Common denominator, excellent. What would the common denominator be? Sine y times cosine y, excellent. So what do I need to multiply this first fraction by? Cosine y. What do I need to multiply the other fraction by? Sine y. Okay. So I still have this sine y sitting out front. Then I'm going to have cosine squared. Oops, these are y's. plus sine squared all over sine y times cosine y. Everybody feel good with that? Okay, what can I do here? Look at the numerator. Yeah, what's sine squared plus cosine squared? 1. What can I do with that fraction now? I can reduce. You guys should try to do 1 through 14.
Okay.
Okay?
Is that due Sunday? Or next?
With the worksheet 1.
Okay.
That sounds right.
Yeah.
Bye, thank you.
We'll see you tomorrow.
Oh.
X day.
Well, I mean, we're not home.
Bye. You're welcome.
Thank you.
We'll see you later.